Last time I talked about the how you define Young's modulus and Poisson's ratio. In terms of tensile test. So I want to just give some values and let you go through calculating that. So finding the Young's modulus and the Poisson's ratio from a tensile test. So let's say that you have a material sample and you put it into tension, let's say 5,000 newtons up and down, and before deformation you have a length of 0.10 meters and a width this direction of 0.01 meters and a thickness in this direction of 0.02 meters. And after the deformation, once it's loaded, you measure the following values. So I'll write this as, call this one capital L, this one capital W, and this one capital D, depth. During loading, you measure a length of 0.10003 meters, a width of 0.00002 meters. No, I'm missing the 1 in there. And then a depth of, well, let's just do the calculation based on these. What? There is enough information. You're a liar. Okay, so what are the Young's modulus and Poisson's ratio for this material? Okay, so take a few minutes and see if you can think through this. I'll give you the definitions. So this is in your notes from last time. So Young's modulus is the axial stress divided by the axial strain, and Poisson's ratio is the negative of the off-axis strain divided by the axial strain. I can't do both. Okay, so sigma xx is equal to 5,000 divided by the cross-sectional area, so that's 0.01 times 0.02. So that is 2.5 times 10 to the 7th. Is that right?
Yeah.
Okay. And then the axial strain is the deformed length, 0.100, were there 3 zeros? Minus 0.1 divided by the undeformed length. And so you get 0.003. But then you divide by 0.1. Oh, okay. Yep. Okay, so Young's modulus then is 2.5 times 10 to the 7th pascals divided by 0.0003. And what do you get for that? So you could say that is 8.3 times 10 to the 10th pascals, or you could say that as 83 gigapascals. So times 10 to the 9 is a gigapascal. So actually, so far the numbers, that's not so bad. Like the Young's modulus for copper, I think, is about 110 gigapascals, so this is in the ballpark of real things. But now things are going to really go off the rails, I'm afraid. Any questions about that calculation of Young's modulus? Okay, so now for Poisson's ratio, we already have one of these strains. We just need one of the off-axis strains. So we have 0.00999. How many nines? 3 nines and then a 3 1. Minus 0.01 divided by 0.01. And what do you get for that? -0.00069. And that's unitless. And so now Poisson's ratio is the negative of the off-axis strain divided by the axial strain, which we got before. And so you get a value of, what is it, a little over 2? That's not possible. Because the biggest possible value of Poisson's ratio is 0.5. And that would be for an incompressible material. So incompressible doesn't mean it doesn't mean that you can't deform it. So in that sense, it's not incompressible. It means that when you compress it or stretch it, the volume doesn't change. Okay, you can't change the volume. Any questions about those calculations? So it's pretty amazing, really, that so to come up with that 6x6 compliance matrix that lets us calculate the strain based on any stresses we know, we have enough information to fill that whole matrix in just based on a tensile test like this. A tensile test and, 3 sets of calipers or whatever. just measure how much it elongates, the force, and then and those two off-axis measurements. Okay, question.
So, are these Young's modulus, is that always XX over XX? I mean,
Well, it's always the axial direction, and people tend to put the x-axis in that direction.
the axial direction is the direction.
The loading direction. Yep. So you tend to make these long, thin pieces, and then put your x-axis along that direction of loading. And, you know, like in Twin Cities Engineering, they do this kind of stuff. Like they've done an analysis like this for the material from the 3D printer. So then you can do analyses of how likely 3D printed objects are to break under different loading conditions and stuff. It's pretty interesting how you can do something that such a simple experiment can give you so much, you know, calculating power. Any other questions? Okay, so the next thing we have to talk about is stress transformations. And that is given a stress tensor in coordinate system A, re-express that stress tensor in coordinate system B. You can do this with vectors, and you can do it with tensors too. So with vectors, we do this by left multiplying a rotation matrix Q. Let me give a definition of how you come up with this rotation matrix. So given coordinate system A and coordinate system B, so this is the original one, and coordinate system B is the new coordinate system. Say that you want to express an A vector in coordinate system B. Okay, so you have a vector expressed in coordinate system A, and you want to come up with the components in coordinate system B. Yep, so and the way you define that rotation matrix is that the columns of Q are the coordinate system axes of A expressed in coordinate system B. It's a little confusing, but I'll do an example. Then the vector expressed in B is equal to Q times the vector expressed in A. Okay, so let's say that this is the vector. It has a length of 10, and its 30 degrees above the horizontal. And let's say that coordinate system A is the standard coordinate system. And we want to, and we'll say that we know the coordinates in this coordinate system, and then we want to re-express that vector in this coordinate system. Yeah, that's B. Okay, so this vector expressed in coordinate system A is 10 times cosine of 30, 10 times sine of 30, so 8.66 and 5. For the rotation matrix, we want to express the coordinate axes of A in B. Okay, so to an observer in B, what are the components of the axes of A? Okay, so to an observer in coordinate system B, what would be the components of the x-axis of A? Yep. So 0, -1, 0, that's the first column. And to an observer in B, what would be the components of the y-axis of A? Positive x, so 1, 0, 0. And then the z's are the same, right? So 0, 0, 1. And so now VB is equal to Q times VA. So 0, 1, 0, -1, 0, 0, 0, 0, 1 times 8.6650. And so you get 5, -8.660. And does that make sense as the components of this vector expressed in this coordinate system? It does. You could think of, so if you put the tail of this vector at the origin of this coordinate system, the angle from the positive x-axis would be -60, and this would be cosine and sine of -60 times 10. Okay? So that's a general definition of the rotation matrix. Usually we can just use, if we want to do rotations of theta about the x-axis, the rotation matrix is 1, 0, 0, 0, cosine theta, sine theta, 0, negative sine theta, cosine theta. To rotate theta degrees about the y-axis, the rotation matrix is cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. And And then to rotate about the z-axis, that rotation matrix is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. And one thing you notice, with almost every thing that you generalize for all the axes, the y-axis always has to be a little bit difficult. It's always got to get its own little thing in there. So notice that you got cosine, positive sine, negative sine, cosine for x and z, but then it's just switched up just a little bit for y. And how do you determine whether theta is positive or negative? So what does it mean to rotate positive theta degrees? Yeah, or according to the right-hand rule is a good way to think about it. So your thumb is in the direction of the axis, and then your fingers tell you the direction of that positive rotation. So that last example, that previous example, this rotation was a positive rotation of 90 degrees about the z-axis. Okay, starting here. Thumb's in the direction of the positive z-axis, and we rotate it that way. Okay, so that rotation matrix should be equal to cosine of 90, sine of 90, 0, negative sine 90, cosine 90, 0, and then 0, 0, 1. So you get 0, negative 1, 0, 1, 0, 0, 0, 0, 1. And that's hopefully what we got. That is what we got by thinking about it the more general way.
Does it matter that you use the shape for the z-axis that you just gave us as opposed to the x-axis for your Q matrix? You see what I'm saying?
No. The
z-axis.
Yep.
Q matrix.
Yep.
That's what you used for what you just did.
Okay, that's what. Did I say something different? That is what this is. It's a rotation about the z-axis.
Yep.
Okay. All right, and so that's how you re-express a vector in a new coordinate system. If you're doing so you can also use Q to express the stress tensor in a new coordinate system. In this case, the stress tensor in the new coordinate system is equal to the rotation matrix times the stress tensor in the old coordinate system times the transpose of the rotation matrix. And your calculator will do that calculation for you. You know, you just have to fill in the rotation matrix, and then it'll do the transpose and do all the multiplications for you. So it's fast and easy. Okay, so let's say that we have, well, let's use the so back to the previous example. Let's say that in coordinate system A, which is like this, the stress tensor is 5, let's say this is all in megapascals, 0, -1, 0, 10, 0, -1, 0, 2. What's this stress tensor in coordinate system B that's oriented like this? Well, Q is equal to 0, -1, 0, 1, 0, 0, 0, 0, 1. So Q transpose is equal to 0, 1, 0, -1, 0, 0, 0, 0, 1. And so the stress tensor in B is equal to 0, 1, 0, -1, 0, 0, 0, 0, 1 times our original stress tensor, 5, 0, -1, 0, 10, 0, -1, 0, 2. Times Q transpose. 0, -1, 0, 1, 0, 0, 0, 0, 1. And if you plug that in, the numbers you get out will be the re-expressed stress tensor in the new coordinate system. So I'll go through that calculation, and then we'll think about why it makes sense next time. Okay. Any questions about that?